To use the library, we do import numpy as np. The fundamental numpy object is the np.array, and we pass this thing a Python list. For now, we'll give it the list of 1, 2, 3. From the output, we know it's a numpy array because it says array here, and only the list of 1, 2, 3 would just output that back. Numpy arrays and Python lists share many qualities, except they also have many differences. For example, if I was to make this item the list of 2 here, that wouldn't work. It calls it a jagged sequence, whereas in Python list, it's actually totally fine with this being the list of 2. Another example, instead of making this the list of 2, if we instead made this the string of 2, well, it's actually okay with that, except then it treats them all as strings because it has to be the same data type throughout. Whereas instead, a Python list would be totally happy with having different types of elements in here. Most of the time, we'll put either integers or floats into this thing, and if I make any of them a float, it has to make all of them floats as well. There also might be times when we instead have arrays of booleans, like true and false. But numpy is mainly for number crunching, hence we usually put numbers in here, and true and false might help us do that. An extremely important concept of numpy is that the arrays have a shape. So if I asked what the shape of this is, it would say 2, nothing. It means that there's just a flat list of 2 things. The shape describes the arrangement of the elements in here. If I was to instead make these items list, we'd have the shape of 2, 1. And this is hard to see with how the array is written right now, but if I was to change it like this, it's written exactly the same way, except we can see we have 2 elements, and those 2 elements are lists. But those lists have only 1 element in them, hence we have 2 and then 1. Now if we try to do something like this, where we added maybe a false here, so the first item is a list of 2 things, and the second item is a list of 1 thing, well, it's not going to like that. It's going to call it a ragged nested sequence. We can't have this sort of mismatching of shape in here. But what it will allow is if I was to add another one down here, we could have a 2 by 2, and we could make as many of these as we want. We could add another false and then false. That's now a 3 by 2 because we have 3 lists, and then each of them have 2 items in them. But again, if I was to make any of these lists have another item here, it's going to call it a ragged sequence. Now we can actually take this one step further. There's no reason these things here have to be elements. In fact, every time we're doing an array, whenever we hit the elements, we will eventually, except we could have replaced this with a list of elements. And so let's make each of these lists, and then can you guess what the shape would be? So we have 3 things. Then in each of those things, we have 2 things. And in each of those final things, we have 1 thing. And if I was to mess up this sort of format on any level, if I added, say, a list here, if I added a list of true, well, then it doesn't match over here. Even if I was to do something like this, where I added this as a false and this as a true, well, it's still not right because this one's in a list and this one's not. Because this one is in a list and these ones aren't. I can fix that like this. And so now it's 3 by 3 by 1. We have 3 things. Each of those 3 things have 3 things. And each of those things have 1 thing. And again, I could add something here, except I have to add it everywhere. And so we still have 3 things here. We have the first one here, then the second one here, then the third one here. In each of those things, we have 3 things here, here, and here. And in each of those things, we have 2 things. And if we really wanted to, since we hit an element here, we could have replaced this with a list. And so finally, I'll just make all of these the list with only holding themselves, so the final dimension is 1. And so now there's 3 things. In each of those things, they have 3 things. In each of those, they have 2 things. And that final list here, well, that only has 1 thing. It might seem pointless that we have that many dimensions, and it might seem pointless that we end the final thing only having 1 thing, because really that's the same as having just the thing itself. Except actually both of these are valid and often used. Now for tutorial purposes, most of what we do isn't going to be using all of these 4 different dimensions. Just know that we might have to do this at some point if you go into machine learning. Firstly, making numpy arrays is kind of a pain in the butt as is, and so what we can do instead is do numpy.zeros, for example. Let's apply a shape, and that'll be a tuple, as we saw. This tuple is exactly like this, and so we can give it a shape of maybe 2 by 3, and so that will give 2 lists of 3 things. And so they're all zeros because we said zeros, and actually we could specify instead that we want the d type equal to maybe numpy.int, and so that would make them integers. Similarly, there's also numpy.ones, so if I was to replace this exact same thing except write ones instead, well, they would be ones. Ones are very useful because we can do simple multiplication by them and get, say, 4s. Now it might have seemed like this times 4 is obviously just a list of 4s, except actually if you did the same thing in Python, where if we had maybe these were 4s and then we had the list of all 4s. This is the equivalent NumPy array, and I can show you it prints out just like that, except if we do this times 4, what that does is actually it's going to keep making this list of 4s over and over again. This is because NumPy is more for doing math, and Python is more for building things. Now, before we discuss more about this kind of multiplication operation, let's show you how to build arrays a little more easily. Let me first remind you of Python's range function. If I was to do range up to 5, well, that's 0 to 5, except actually it's not really 0 to 5. This converted to a list, then you'll see it's really just 0 to 4. Now we have basically the analogous thing in NumPy, which is numpy.arange, the A for array, and if I gave this a 5 here, well, we see we have that exact same thing, but a NumPy array. And just like Python, if I was to switch this to maybe a 2 in front, I could get the numbers 2 to 4, and here it's exactly the same thing. Now if I was to change this to 1 and then 11, that'll be the numbers 1 through 10, and we could also do a number here which is step, and so maybe I did 2, and so actually it's stepping by 2s, by starting at 1 and then going all the way up until 10, because that's 11 minus 1. We could of course do the exact same thing in NumPy, and so if I made this 1, 11, and 2, we would get the exact same NumPy array. Now many functions in NumPy take an argument as a shape. We set shape equal to some tuple, and then maybe make it equal to, well, if this has 1, 2, 3, 4, 5 elements, then we could make it maybe a 5 by 1 element array. Except actually this one doesn't take a shape element, but we can do something else like this. All NumPy arrays have this function called reshape, and so this does take a shape, and so we'll give it, if this is going to be 5 elements, then we could make it 5 by 1. And so here we can see we have 5 things, and then each of them only have 1 in them. Now remember, when we're doing reshape, we better actually have this number of elements is equal to the number of things we have here. If we had maybe 6 by 1, well, that's not going to work because we only have 5 elements in here. We see you cannot reshape an array of 5 into 6 by 1. If we have 6 and then 1, that means we're expecting 6 elements, and if we instead did something like 6 by 2, well, that's not going to work because that's expecting we have 12 elements, where again we only have 5. So just be cautious that when you're doing reshape, it's only going to work if the exact number of elements lines up, and it's always going to be all of these numbers multiplied by each other is the number of elements that we'll have, and over here, well, that's up to how you made the array. In NumPy, we also have this awesome thing called linspace, and so what that does, let me just show you with an example. If I do 1 and 3, then I give the number 5 here. Well, that gives me 5 elements in the range of 1 to 3. And so here we have 1, 2, 3, 4, 5, except they're floating point values in the range of 3. And they're evenly spaced, so we didn't have to think about the spacing. We just got 5 elements between this range, and notice actually that the 3 is included by default, whereas in the range function, it's usually not. There's lots of other ways to make NumPy arrays, but the last one I'm going to show you here without doing any sort of addition or multiplication is something called numpy.I. And so what this does is gives us the identity matrix, and if I specify here, this actually it has to be square, and so we have 3 by 3, and we get 1s on the diagonal. Now let's get used to multiplication, addition, and other sorts of operations on these arrays. So let's look at now just an array of say 1, 2, 3. As we saw, if we multiply this by a number, then we do it element wise, and so this is that times 3 times 3 and times 3. We also have supported the common operations like division. This is the floating point division, so these are floats. We could have made integer division, and so these are all integers. We could do subtraction, and we also get addition. Regardless of the shape of this array, even if it was the list, and inside that I could have a crazy list like this. This is a totally valid array. It's just 3 by 1 by 1. If I was to do this, it's still going to go into the bottommost dimension and actually add this to each of the elements, and it'll do that no matter what of these common operations we choose to do. But I don't really like this array, so we're going to work with instead the numpy.arange of 4, and then we'll reshape that into 2 by 2 so that we just get 0, 1, 2, and 3. Now I'm going to copy this and then put it down here so that we can do various things to this and see what happens. Maybe if we multiply it by the numpy.array of 1 and then 4, okay, we see something weird here. Actually, what we can picture is putting this 1 and 4 first on top of this 0 and 1, and the 1 would line up with the 0, we get 0, the 4 would line up with the 1, and we get 4, and then after we put this 1 and 4 onto the 2 and the 3, and so 1 and 2 makes 2, and 4 and 3 makes 12. We could have replaced this with any operation, and this would have been the same if this was plus. So we get 1 and 0 is 1, we get 4 and 1, we get 5, and then we put it down on the second thing, we get 1 and 2, we get 3, and 4 and 3, we get 7. You might be wondering why this actually actually added it like this was a row and it put it on top of this row and then on top of this row, there's no reason it couldn't have just put it as a column and we'd actually get a different answer if we put it as a column here and then as a column here. If we wanted to specify this, we'd actually have to make this a different dimensional array. If we instead added this, and now actually we can think about it as it's basically a column like this, well now we actually would get that answer. So we get 1 and 4, we put that onto this array, we get 1 and then 6, and then we put this column onto this one, we get 1 and 1 is 2, and then 4 and 3 is 7. And this is what we call broadcasting in Python. This array gets broadcast across this column as well. And honestly, it's a very, very confusing topic. I'm going to stick to what I think is really important out of it, which is mostly working with arrays of one dimension. So if we have the list of 1, 2, 3, or the array, and then we add that to the numpy.array of maybe 4, 5, 6, well, that's going to do 1 and 4 is 5, 2 and 5 is 7, 3 and 6 is 9. The only other thing you might have expected is to have the same thing as Python lists, which is 1, 2, 3 plus 4, 5, 6. That actually concatenates the lists, and if you want to look up the function concatenate in NumPy, you would do something similar. Now, what we don't know how to do yet is actually look at the individual elements and look at this array, for example. We don't know how to grab the first column, or maybe the first row, the second row. We don't know how to get any of the elements, like this element here, and so what we're going to do now is show you how to do that, called indexing. If I set this equal to something, maybe I'll call it A. So let's grab the 3 here. To do this, we do A, and then we do square brackets like Python, except we have more flexibility. And so here I can specify to get this 1 and then 1. And that's because, let me just show you what A1 is at first. Well, A1, this is saying, okay, first I want either this or this. And you gave me a 1, and so this is represented by 0, it's 0 indexed, and so you said 1. Okay, so you want the NumPy array of 2, 3, that's the first row. Actually, I can specify more than that. I can give the 1 here, and that's basically saying, oh, okay, of this thing, of this row, you want not the first thing, you want the second thing. That's why the 1 says. And so this would get the 3. We also can do this thing called colon, and that says all of them. So if I do this, that's specifying, oh, okay, for the rows, you want actually all of the rows. So what is this thing? Well, all of the rows, that's just the whole array, that's the whole thing. Except again, I can specify from this, maybe I only want the first column inside each of these things. Well, that is the first column, because it's saying, of the 2 rows, what do you want for the columns? Well, I want 1. I could also have asked for the first thing, and so that's the first column. I could also do this, which says I want all of the rows and all of the columns. Well, that's again exactly the same thing as asking for the whole thing. It's the same thing as just asking for all of the rows, because that's everything. This of course works for NumPy arrays that are even simpler, as well as ones that are more complex. If we had the NumPy array of 1, 2, 3, so if we s colon here, well, that's the same as all of them. We could get a particular one, like the 2, we would get this way. I'm now going to show you why we need these concept of NumPy arrays with trues and falses. So if we had something that looked like this, where we had true, and then false, and then false, and then true, well, we can think of this as yes or no, as in, yes, we want this, yes, we want this, no, we don't want this, no, we don't want this. So if I had something like A here, I'm going to give it this array itself, gives us the array of 0, 3. And that's simply the array, except we only have the true elements here. If we instead change this to a true, then we'd have the array of 0, 2, and 3. Notice that when we do this, we actually get an array of, it's only ever going to be one dimensional. We'll have some amount of elements in just one long list. And that's because when we do something like this, it's kind of hard to preserve the shape. Now this is really what's going on, except we don't really do this in practice. This whole NumPy array, we're never going to write something like that, and we'll never write this again. What we will do instead is say something like maybe A greater than 1.5, and that is going to produce one of these arrays on the fly. So we can see here, comparing to A, well, this is false and this is false, but this is true and this is true. It produces this array on the fly. If we put that in A, so if we do A and then the indexing here, we know that that's the same thing as before. This is what is produced in there, and so we can just get the array of 2, 3, which is what actually follows from this. But anything more complicated than this, I would just start to use pandas. I think it's better at this, so check out my tutorial if you don't know pandas. If I did numpy.random.normal, for example, well, this is coming from a normal distribution, and it doesn't really matter if you don't know what these things are, but I'll just give it a mean of 1 and a standard deviation of 2. And then if we output the size here, that actually, the size really just just means the shape, and so we'll give a tuple here. Maybe we'll do 3 by 4, and so we have a 3 by 4 array. Each of these are coming from the random normal distribution of a mean of 1 and a standard deviation of 2. If you follow any machine learning tutorial, you'll probably run into the concept of random noise at some point. Now we have to finish this off with talking about the Numpy vectorization. Everything in Numpy is vectorized unless you explicitly tell it not to, which is a problem. And so please do not write a function that does something like this. And so we'll make a function, we'll call it define squared array, and then it's going to take an array called A. Now before we do this, I need to show you something very briefly. That is, if we had the array A, as we did earlier, well, this thing, you can actually change its elements. So I could set A00, if I set that equal to 5, and I'm actually going to do that down below so we don't get rid of that. If we do that, then A, well, it just set that element equal to 5, so we can adjust this. If we are writing this squared array thing, what we could do is just first get the dimensions of A, and we're going to assume that it's two-dimensional like this, as in it has a shape of some number by some number. Something like maybe 3 by 4, 5 by 7, or something like that. So we could get this very easily by first dim is equal to A.shape sub 0, and then second dim is A.shape sub 1. And if we don't see this, we could just do A.shape sub 0. That gets the first thing, and this is the second thing. They happen to be the same number, but the 0 was the first was the second. And so what we could do is iterate over this. We could say for I in range of the first dim, and then for j in the range of the second dim, well, we could just set A sub I sub j, that's that element of interest. We could set that equal to A sub I sub j times A sub I sub j. It's setting that element equal to itself by itself, which is squared. Okay, so this would work if we had, and let me just kill what we have down here, if we have the array of A, and if we were to call squared array of A, that will work. It's true, it makes the square of the array, that's fine. Except this is not how we'd want to do this. And we instead could do the exact same thing, except we'll say define squared array, and then we'll just write vectorized to show you that it's vectorized. What we would do instead is just return, it depends what our function is trying to do, but this one, we would just do A times A. If we have A here, and then if we do A times A, well, that is going to do exactly what we wanted it to anyway. So please, if you ever start writing for loops when you're working with Numpy, really think and Google if you actually need to do that, because you probably don't, and it really hurts if you do it and you don't have to. Now let me summarize everything concisely and explain simply. So import numpy as np is how we import the library, it's how we use it. Numpy has this thing called an array. Arrays store elements, and it could store numbers, it could also store true and false, but usually we store numbers. It can have a different shape. This is 3 things, and so the shape is 3, and the shape here of this array, well, we can see we have 2 things, and then in each of those things we have 3 things, 1, 2, 3. So this shape is 2 by 3. And we can do this however much we want. We could do 4-dimensional things where we had the first thing is 3 things. We see 1, and then we see 2, and then we see 3, and then okay, we go inside that. What's the closest thing inside? Well, we go in one of these things and we see this. We see there's 1 thing, we see there's 2 things, we see there's 3 things. That explains the other 3 here. We go inside one more step, and so we see, oh, okay, there's 1 thing, there's 2 thing. All right, that's the 2, and inside the last thing, we see that there's 1 thing. Comparing this to base Python, and here as a Python list, we're okay with it being an integer and then a string, and this could have been whatever we wanted. It could have been a list or whatever, except in Numpy, we have to make sure that we have just all of the same data type, as well as if any of these started to look a different way. If we instead had maybe 2 things in this final thing, which isn't matching because the rest of them, in each of them, we had 1 thing here, well, it's not going to like that. It's going to call it a ragged sequence. It has to match, and so it's got to look all the same throughout of it. There's many different ways to build NumPy arrays, and one of them is numpy.zeros. We specify the shape that we want, and so we get 2, and then by 3, and then dtype we specify if we want integers. By default, it's probably going to be floats. We could also do numpy.ones, and so we give it a shape, and then specify ints if we want, and then we could just multiply that by value if we wanted, because it's going to do it element-wise. We'll do 4 times 1 times 1 times 1, and then that gives us all 4s. In comparison to Python, Python's about building things, and so this isn't going to do a bunch of math here. It's just going to assume you wanted to extend this list a bunch of times. If you wanted to do something like this, look up numpy.concatenate. Now, similar to the Python range function where we can specify a start, a stop, it actually goes to stop -1, and then a step. Well, here we get 1, then 3, 5, 7, 9. It doesn't do 11 because it's only going to go up to 10, and since 10, well, we're going up by 2s, it's just going to skip over and not do it at all. In NumPy, we can do the same thing. This start end and stop does exactly the same thing. And what this does is it's going to specify to make sure all of the elements that we made here are arranged in this particular shape. Except what it's not going to do is allow there to be different elements in here than makes sense for here. Because here we actually saw there's going to be 5 elements here, 1, 3, 5, 7, 9. Except here 6 by 2, well, this is asking there to be 12 elements. There's going to be 6 rows and 2 columns makes 12. Just 6 by 1 or even 6. These aren't going to work. It needs to store 5 things. We could do 5, maybe 5 by 1. We also have linspace. Linspace is nice for making different floating point arrays. So we specify a start, an end, and then we say how many we want in here. It says we want 5 values, so we did evenly spaced between 1 and 3. We saw this thing called numpy.I. It's called the identity matrix in linear algebra, and basically it's just diagonal ones where everything else is a 0. We looked briefly at the concept of broadcasting in Python, and so here, if I'm adding this array, these arrays are exactly the same thing, except then we add this array where if we have it look like a column here, we'll put that here, so we have 0 and 1 is 1, we have 4 and 2 that makes 6, and then we have 1 and 4, we'll put it on top of this column to get 1 and 1 is 2, and 4 and 3 is 7. And again, in contrast to Python, we're not adding lists like this. Look up numpy.concatenate instead. Here we looked at how to access different components of numpy arrays, and so we could do maybe a sub 0. That'll get us the first row of this thing because the first possible dimension is either this or this, and we chose the first one to get this. And then from here, we can do, maybe we want all of the components. That's actually the same thing, except this could be useful if we wanted to say maybe, well, actually, I want just all of the rows, except then I only want the first column. The colon says, oh, I want all of the rows, except on the second thing, I say, oh, actually, I only want the first thing. You could also ask for any individual component, so maybe we wanted the first thing, like A00, or A01 is going to be, want the first row, and then the second value of it. This, of course, works for even easier examples where we had just 1, 2, 3, and we wanted the second element, we got the 2 there. Here we saw how we might want to use Boolean arrays. So if we did A is greater than 1.5, remember A is this array right here, well, A greater than 1.5, that produces element-wise whether this condition is true. So here, 0 is less than 1.5, so it's false, 1 is less than 1.5, so it's false, but these are true and true. And we can use this because if we pass this into the square brackets of a numpy array, well, that just gives us back the elements flattened into this one long list here of where it's actually true. In many applications, we'll need random arrays, and so we pick some distribution. Numpy has many different ones. We give parameters to that distribution, and then we specify the shape that we want to give to that. And most importantly, we talked about the concept of vectorization, where if you're ever writing code that looks like this for I in range or for j in range, or you're doing a bunch of loops, you're probably doing it wrong. You should be doing stuff like multiplication, addition, or other sorts of numpy already implemented functions. If you found this tutorial helpful, please subscribe and like the video. It helps a lot, and I'll see you in the next one.